Hi everybody, so we're going to start looking at actual application questions for these differential equations. So first of all, this is going to be a super long video, so if you need to watch it in chunks, I suggest doing that. You've got a long weekend to get it watched anyway, so you might have to pause or fast forward at some points, but you need to watch the whole thing. It's really important. And second of all, these are super important because these are potential free response questions from the AP exam, so you want to know how to do these. Alright, so consider the differential equation dy dx equals negative xy squared over 2. Let y equals f of x be the particular solution to this differential equation with the initial condition f negative 1 equals 2. So the first thing we're going to do is sketch a slope field. So we practiced this in class already, so let's go ahead and do this. The first thing we should notice is that the top here is x times y. So any place that we have x or y equal to 0, we are able to say that the slope is 0 right away. So I'm going to go do that first. So anywhere on the x or y axis, we have a slope of 0. So I'm going to go ahead and put those in because that takes care of 6 of the points for me. So now I just have to do these other 6 on a point-by-point basis. So if I do the point 1, 1, that's going to be negative 1 times 1 squared, which is negative 1, over 2. So that's going to be a slope of negative 1/2. For the point 1, 2, let's see, that's going to be negative 1 times 2 squared, so I'd have negative 4 over 2, which is going to give me a slope of negative 2. The point 2, 1, I would have negative 2 times 1, so negative 2 over 2 is going to give me a slope of negative 1. For the point 2, 2, I would have negative 2 times 2 squared, so I'd have negative 8 over 2, which is going to give me a slope of negative 4. Again, don't necessarily care too much about the steepness. You can tell they're a little different. They're not exact. I'm not super worried about that. As long as we know they're negative, we're okay. For the point negative 1, 1, we would have then a positive 1 times 1 squared, so we would have a positive 1/2 for our slope here. And then for the point negative 1, 2, we would again have a positive then times 2 squared, which is 4 divided by 2, so this is going to be a slope of positive 2. Alright, and that's what our slope field looks like. So let's take a look at part B. So part B says write an equation for the tangent line to the graph of f at x equals negative 1 and use it to approximate f of negative 1.2. So the first thing we need to remember is that if we're trying to write the equation of a tangent line, we need two things. We need a point, and we know that we need the slope. Alright, so let's see. The point, it's saying at x equals negative 1. So we need to kind of go back up here, and we need to recognize that they gave us this initial condition of negative 1, 2. And so that's the point we're going to end up using down here to write our tangent line equation. Alright, and then for slope, well, we were given the first derivative, and we know that the derivative is the slope of the tangent line. So we were given dy dx. And we're going to evaluate it then at the point negative 1, 2. So that means we're going to have the opposite of negative 1 times 2 squared over 2. So all I'm doing is plugging it in. We can't see that, sorry, it's off the screen. I'm plugging it into my equation that they gave me. So that becomes a positive 1 times 4 divided by 2. We get a slope of 2. So if we're going to write the equation of the tangent line then, we can use point-slope form because that's the easiest. So let's see, we're going to have y minus 2 equals 2 times x plus 1. And there's the equation of our tangent line. Now it says we have to use this tangent line to approximate f of negative 1.2. So we're going to have to kind of backtrack a little bit and think back to when we did linearizations. So when we did linearizations, we said we're going to swap out the y and turn it into L of x. And we're also going to move that constant over. So now it becomes L of x equals 2 plus 2 times x plus 1. So we're going to substitute in negative 1.2. So we have 2 plus 2 times negative 1.2 plus 1. So let's see, we'd have 2 plus 2 times negative 0.2, which really means 2 minus 0.4. And so we get that L of negative 1.2 is really 1.6. So if we're trying to approximate f of negative 1.2, negative 1.2, that's approximately 1.6. All right, the next part of this question says to describe all the locations in the xy plane for which the slope of y equals f of x is positive. So we're going to do this by looking at our slope field first. So if we look here, we can see just by looking that the slope is positive at these 2 points. All right, which means as long as x is less than 0, then we have these positive slopes. But the one exception is right here, okay? Because right here we have a slope of 0. So we have to be careful when we write our answer. Let's take a look down here. So the slope of y equals f of x is positive for all points xy such that x is less than 0. All right, but we said that works for these 2 points, but right here x is less than 0 also, and we know that the slope was y. So really what we need to say is it's all points xy such that x is less than 0 and y is not equal to 0. All right, so we got that by looking at our slope field, but we can also look at the equation that we were given. So negative xy squared, we know that regardless of what y is, that's always going to be positive because it's squared. So really we're just looking for where negative x is going to be positive, which is for negative x values, except for when y is equal to 0. All right, so you should be able to do that really from your equation and from your slope field. All right, let's go ahead and keep going here. So these 2 parts here are still a continuation of the question we were just doing, because you can see here it says part D, it's not a new question. So it says find the particular solution to the differential equation with the initial condition f negative 1 equals 2. So I'm going to go ahead and write what our differential equation was. It was dy dx equals negative xy squared over 2. All right, so we should be getting much better at this and much quicker at this. So I'm going to go ahead and first separate my variables. So that means I'm going to have dy over y squared equals negative x over 2 dx. This is a very important step to show, all right? Questions like this on the AP exam, if you don't show the separation of variables first, they don't even continue looking at your work and you just lose all 6 points on it. Okay, so you don't want to do that. Please, please, please make sure you show this step. All right, and now we're going to do the integral. So hopefully we're getting better at the fact that dy over y squared, the antiderivative of that, would be negative 1 over y. And then the antiderivative of negative x over 2 would be negative x squared over 4 plus c. And so now we're going to go ahead and solve for c. We were told that we've got this point negative 1, 2. So that means we're going to have negative 1/2 equals negative 1 squared over 4 plus c. So negative 1/2 equals, this becomes then a negative 1/4 plus c. And if I add 1/4 over to the other side, I would have negative 1/2 plus 1/4. That would end up being negative 1/4 for our c value. So I'm going to go back up here, but I'm going to go all the way up to the top so I've got some room to work. But negative 1 over y equals negative x squared over 4 minus 1/4. And we can see already that that's a common denominator, so I'm going to go ahead and put those together. So negative x squared minus 1 over 4. I'm going to get rid of the negative sign by multiplying both sides by negative 1. So 1 over y is equal to x squared plus 1 over 4. And now I can just take the reciprocal of both sides, and I get that y is equal to 4 over x squared plus 1. Now, I always like to go and double check my initial condition. So if I plug in negative 1 for x, negative 1 squared is positive 1, plus 1 is 2, 4 divided by 2 is 2, and that's what my initial y value was. So it's a pretty easy way for me to check and make sure that I've got the right equation. Okay? So the last thing we have to do here is it says find the second derivative in terms of x and y. So I'm going to go ahead and rewrite what our first derivative was. So dy dx is equal to negative xy squared over 2. And something I want you to make a note of right here is that in order to find the second derivative, we're going to need implicit differentiation. All right, our derivative here is in terms of x and y. So we're going to need to use implicit in order to take this derivative. So let's see here. Before I even take the derivative, I'm going to take this negative 1/2 and kind of pull it out and make it negative 1/2 times xy squared, because then I can kind of ignore the negative 1/2 and just use product rule in here. So I'm going to do it in a different color. Let's look. The second derivative then is going to equal, I'm just going to put this negative 1/2 out front, and I'm going to worry about the product rule. So product rule says I'm going to take the first, which is x, the first function, and multiply by the derivative of the second function. Well, the derivative of y squared is 2y. But we need to remember that since it's a y, we also have to have dy dx. And then plus, let's see, product rule says the first times the derivative of the second plus the second, which is y squared, times the derivative of the first. Well, the derivative of the first is just 1, and so there's our product rule there. Now we're going to need to do a couple of things here to start to simplify. So I'm going to leave the negative 1/2 on the outside, and I'm going to turn this into my 2xy, because I can just multiply those together. Now here's the weird part, or well, different part. Dy dx, we know what that is, right? It's actually this negative xy squared over 2. So I'm going to go ahead and put that in place of dy dx. So negative xy squared over 2, and then this is plus y squared. We can go ahead and keep simplifying. The 2's are going to cancel right here. So we would have negative 1/2. This would become negative x squared y to the third plus y squared. And then we can go ahead and distribute the negative 1/2 inside. So we would have a positive 1/2 x squared y cubed minus 1/2 y squared. And that would be our second derivative then. Oh, and you guys can't see any of that. I got a little involved in myself there. I'm so sorry. I hope you were still able to follow along with what I was saying, but here's the work that goes along with the words that I said. I'm so sorry, you guys. I got involved in that problem. But hopefully that makes sense. Okay. Again, I know that this is a long video, so bear with me. If you need to take a break now because we finished the first problem, take a break and come back to the video. All right? So question 2 is a word problem. Everybody's favorite, right? So the rate at which a baby bird gains weight is proportional to the difference between its adult weight and its current weight. At time t equals 0, when the bird is first weighed, its weight is 20 grams. So before I even keep going, I'm noticing then time t equals 0, the weight is 20 grams. That's my initial condition, right, the initial weight is 20 grams. So if B of t is the weight of the bird in grams at time t days after its weight, then dB dt is 1/5 times 100 minus b. So hopefully you guys can look at this dB dt and you can recognize that that's a differential equation. All right, we've been working with that a lot. What you should also notice is that dB dt is going to be the rate at which the weight is changing in this bird. Okay, so it says let y equal b of t be the solution to the differential equation with an initial condition of b of 0 equals 20. So that's that initial condition that we pointed out up here. So part A says, is the bird gaining weight faster when it weighs 40 grams or when it weighs 70 grams, and explain your reasoning. So it's asking if the bird is gaining weight faster at these different weights. This is that rate, which means we really just need to be looking at dB dt. And since they give us these weights, the weights are our b values. So we're going to evaluate it at b equals 40 and at b equals 70. So dB dt evaluated at b equals 40 means it's 1/5 times 100 minus 40, which means 1/5 of 60, which we know is 12. And then we're going to go ahead and do dB dt when b is equal to 70. So that means 1/5 of 100 minus 70. So 1/5 of 30, which we know is 6. All right, one important thing to think about, this is a word problem, right? So we know that these numbers here are going to have units on them. So since this is the rate at which the bird's weight is changing, we know that dB dt when b is 40 is 12, but it means that it's 12 grams per day. So when the bird weighs 40 grams, its weight is changing at a rate of 12 grams per day. When we evaluated it at 70, we're saying that when the bird weighs 70 grams, its weight is changing at a rate of 6 grams per day. Sorry, I know that kind of got squeezed in there and cut off a little bit, but hopefully that makes sense to you. So now what it's asking is which one is faster, and to explain our reasoning. So we're going to say then that the bird is gaining weight faster when it weighs, well, let's see which one's bigger, 12. So when it weighs 40 grams, because we know that the rate at 40 is greater than the rate at 70. So the way we're going to show that is dB dt when it's evaluated at b equals 40 is greater than dB dt when it's evaluated at b equals 70. Don't forget to do the explanation part, okay? You're going to get more points for the explanation than you are for just writing an answer. So when they grade this, they're going to be looking at, did you show the work? Did you know you needed to evaluate it at both spots? And then were you able to reason through and see which one was actually the bigger value? Okay? Now it's asking us to find the second derivative in terms of b. So we just did this a little bit ago, so we should be able to quickly do it. But dB dt we know is equal to 1/5 of 100 minus b. So if we want to do the second derivative, well, this 1/5 is a constant, so we're going to bring it out front. And we know that the derivative of 100 is 0. The derivative of negative b would actually be a -1, and then we know it's times dB dt, because we need to use that implicit differentiation again. So this really becomes -1/5, and then we need to substitute in the dB dt again, which is 1/5 100 minus b. and then we can just multiply those 1/5 together. So it becomes a negative 1 over 25 times 100 minus b. That would be our second derivative here for the birds. All right, then part C is very similar to some of the problems that we did in class when we were practicing solving differential equations, but it's a good one to have in your notes. So use separation of variables to find the particular solution to the differential equation with a condition b of 0 equals 20. So we need to start with our derivative, so db dt is equal to 1/5 of 100 minus b, and we need to separate our variables. So we're going to have db over 100 minus b equals 1/5 dt. Again, very important to actually show the separation of variables. The directions even say it for you. All right, so then we're going to take the integral. And we know that the antiderivative of db over 100 minus b is the natural log of the absolute value of 100 minus b. And we know that because of chain rule, it should be negative. So because it's not, we're going to need to put that negative sign in front. And then the antiderivative of 1/5 would be 1/5 t plus c. So we're going to go ahead and use our initial condition of 0, 20 and figure out what our c value is. So the negative natural log of 100 minus our b value, which is 20, equals 1/5 times 0, which is really just 0. So that's going to be our c value. So we're going to end up getting the natural log, negative natural log of 80 is equal to c. So I'm going to go back up here then, and let's see, the negative natural log of the absolute value of 100 minus b is equal to 1/5 t minus the natural log of 80. And now we need to isolate the b, okay, because we need to solve for the original equation. So if we divide both sides by a negative, we get the natural log of the absolute value of 100 minus b is equal to negative 1/5 t plus the natural log of 80. And now we need to get rid of the natural log. So we know that that means we're going to go ahead and put an e on both sides. And all of this stuff is going to become the exponent for our e. The only way to undo a natural log is to turn it into an exponential. So e to a natural log ends up canceling, and we have the absolute value of 100 minus b. And that's equal to e to the negative 1/5 t plus the natural log of 80. So the absolute value of 100 minus b is equal to e to the negative 1/5 t times e to the natural log of 80. And hopefully you guys are getting better at seeing this, but I'm just showing it to you anyway. This ends up turning into just an 80 then. So the absolute value of 100 minus b is equal to 80 e to the negative 1/5 t. We know that to get rid of the absolute value, we need to put a plus or minus. So 100 minus b is equal to plus or minus 80 e to the negative 1/5 t. And now we need to keep solving for b. So that means we're going to subtract 100 and then divide by a negative. So I'm going to do that kind of in one step here. So b is equal to plus or minus 80 e to the negative 1/5 t, and then we subtracted 100 but divided by a negative, so this becomes a plus 100. All right, but now we have to consider our initial condition. Our initial condition was that when t is 0, b has to be 20. So if we substitute a 0 in for t, we would have e to the 0, which is essentially 1, right? So we're either going to have positive 80 plus 100, or negative 80 plus 100. Since we want our b value to be 20, we know that we want that 80 to be negative. So our final answer, sorry I kind of ran out of room, but our final answer is going to be b equals negative 80 e to the negative 1/5 t plus 100. That is going to be our final answer. I know I kind of ran out of room and had to squeeze it over there, but hopefully that makes sense, especially because we did some of those in class together. All right. Again, I know that this is getting long. Please continue to bear with me. If you need a break because we finished that question, take a break. Okay, we've got one more question we've got to do together. So question 3 gives us this differential equation, and the first part asks us to go ahead and draw the slope field. So we're going to go ahead and do that. And unfortunately, we notice that it's not quite as easy as the last one, so we're just going to kind of have to go point by point. So if I plug in the point 0, 0, I would have 0 plus 0 minus 1, and I would have a slope of negative 1. If I plug in the point 1, 0, that means I'm going to have 1/2 plus 0 minus 1, so that's going to be a slope of negative 1/2. For the point 1, 1, I would have 1/2 plus 1 minus 1, so I would have a slope of positive 1/2. Oops, that looks more like positive 1, but that's okay, close enough. For the point 1, 2, let's see, I would have 1/2 plus 2 minus 1, which means this is going to end up being a positive 3/2, so a little bit steeper than positive 1. All right, let's see, the point 0, 1. Oh, by the way, this might be a good point for you to just fill in the slope fields here and then just go ahead and skip this part to save yourselves a little bit of time if you want, rather than listening to me reason through them all. But let's see, 0, 1, so that's going to be a 0. 1 minus 1 is 0. 0, 2, so 0, that's going to be a slope of 1. Negative 1/2 plus 0 minus 1, so negative 3/2. Negative 1/2 plus 1 minus 1, so negative 1/2. And then, let's see, negative 1/2 plus 2 minus 1, that's going to be a slope of positive 1/2. Okay. So there's our slope field. Now the next part says find the second derivative in terms of x and y. Describe the region in the xy plane in which all solution curves to the differential equation are concave up. So first thing we're going to do is find the second derivative. So d2y over dx squared is going to equal, let's see, here's my equation up there. So the derivative of 1/2 x is 1/2 plus the derivative of y, which is 1 dy dx, minus 1, and we're going to go ahead and substitute in dy dx. So, oops, not minus 1, that's a 0. Hopefully you caught that. The derivative of negative 1 is just 0. Sorry about that. So 1/2 plus, let's see, our dy dx is 1/2 x plus y minus 1. And now we're just going to go ahead and simplify. We've got 1/2 and negative 1. So we get a 1/2 x plus y minus 1/2, and this is our second derivative. All right, so now it's asking for every place that the solution curves are concave up. So what we need to remember is we need to think back to what it means to be concave up. We know that for a function to be concave up, the second derivative has to be greater than 0. So our second derivative is equal to 1/2 x plus y minus 1/2. And we want that to be greater than 0. So what I'm going to do here is I'm going to go ahead and I'm going to solve for y. So I'm going to have y, if I subtract the 1/2 x over, it'd be a negative 1/2 x, and I would add the 1/2. So I would have y is greater than negative 1/2 x plus 1/2. Well, that means that anything that's above this line is going to be positive, and that means that anything that's above that line is going to mean that it's concave up. I just said it's going to mean a lot. Sorry about that. Okay, so what we're going to write is solution curves will be concave up above the line y equals negative 1/2 x plus 1/2. All right, and again, it's concave up there because we need the second derivative to be positive. Okay, we have one more part and then we are done, I promise, okay? So let y equals f of x be a particular solution to the differential equation with the initial condition of 0, 1. Does f have a relative minimum, a relative maximum, or neither at x equals 0? And justify your answer. Now, this is where we have to be really careful and we have to be smart. You do not have to solve this differential equation, okay? Don't go through all of that work. We have to remember that there are other ways to determine whether a function has a min or a max or neither. And we need to do that by looking at the first and second derivative. So we're going to look at our first derivative, dy dx, and we're going to evaluate it at the point 0, 1. So that means we're going to have 1/2 times 0 plus 1 minus 1. And we get that the first derivative is equal to 0. Well, we know that anytime the first derivative is equal to 0, we have a horizontal tangent. So we have a horizontal tangent at x equals 0. That's important because we know that there's going to be a min or a max there. We know that there's going to be something special. So in order to figure out whether it's a min or a max, or possibly still nothing, we need to look at the concavity. And we decided that the concavity is determined by the second derivative. So I'm going to go ahead and look at my second derivative, which we just found in the last problem. So I'm going to evaluate that at the same point, 0, 1. Sorry, I kind of squeezed that in there. So let's see, this was it. So 1/2 times 0 plus 1 minus 1/2. So we get that the second derivative at the point 0, 1 is 1/2, which is greater than 0. That means then that this function is concave up. So since the first derivative is 0 and the second derivative is positive, the function is concave up, and it means that we have a relative minimum. So now we need to go ahead and write our explanation. So f has a relative minimum at x equals 0 because the first derivative, so dy dx, evaluated at the point 0, 1, is equal to 0, and the second derivative, evaluated at the point 0, 1, is greater than 0. All right, I know that was really long. Thank you for bearing with me. I hope that you guys took some breaks while watching it, but it's a lot. It's a lot of really good, important stuff, and when you guys come back to class, we are going to do tons and tons of practice. So if you need to rewatch portions of it, do that. Come in and see me if you need me, and I will see you guys later. Enjoy the rest of your weekend.